First on our program is today's keynote presentation by Anders Ynnerman, who will tell us about exploration. So Anders Ynnerman is since 1999 a professor in scientific visualization in Linköping. He is also the director of Norrköping's Visualization Center, C. And well, his research spans a range of topics in computer graphics and visualization, and has earned him some awards, a number of awards, including the King's Medal in 2017 for his contributions to medical image science. So we are glad that you could come, Anders, and look forward to your talk.
Thank you. Yeah. Thank you very much, Anders. There are so many Anderses here. You will hear about a few during the presentation as well. It's great to be here. Appreciate the invitation. It's a couple of times I've been invited and haven't been possible for me to come down, but it's great to be back in Lund, and it brings back memories. I was an undergraduate student here. I reminded Anders that I had him as a lab assistant when I was an undergraduate student. He did not remember that, but anyway, yeah, so it's great to be back. And this building did, of course, not exist back then, but it was across the street where I did all my lab assignments. What I'm going to do today is to, for the next hour or so, maybe an hour and a half, if you have a no-show, I can continue for an extra half hour. I'm going to talk a little bit about visualization. I'm going to talk about the possibilities that we have using visualization in a number of different domains. I was intending to talk primarily about the work that we do in space and astro, but given the audience here, I will share my time between a couple of different domains. And so it's going to be a bit of a journey. But the journey is connected by this concept. And this is the only thing I want you to remember and to be able to pronounce is exploration, and I will tell you what that means in a little while. My wife is American and she hates me because I invent new words that don't exist, but that's the way I work. Now, this is the Norrköping Visualization Center. This is where my home base is. It's a pretty unique place because it's a new campus. It's sorting under Lund University, but it's in the city of Norrköping in the region of Östergötland, and I challenge you to pronounce that with all the umlauts in there. But what we have done is that we have taken the old environment, which used to be textile industry, and turned that into sort of a knowledge-based area. It's sort of a transition that took place maybe 20 years ago. And now we've completed that. So the way it looks like now, so this is the Visualization Center. Here you have, this is the research unit. We're about 70 full-time equivalents working on research in visualization and graphics. I have this office here. This is the smallest window right here, facing the river, which is quite nice. But apart from doing research, we have also opened up the center to the general public. So we have about 150,000 visitors per year coming through our center. And to be able to provide them with an experience and entertain them, we have a production unit that's taking research results from many different scientific disciplines and turning it into interactive installations that we are showcasing in our exhibit area, which is right here. We also have a dome theater, and I will talk a little bit more about that, seating about 100 people. And it's fully stereoscopic, and it's just being upgraded right now, and I'll talk more about that later. We also have about 10 spin-off companies from the environment, and we have Rise Interactive is sitting over here, more research, education, a number of very good students that are going through the system. So all in all, about 150 people working in this environment, all focused on media, visualization, and data, which is kind of interesting. So when you come to the exhibit, this is what it looks like. Everything ranging from exhibits about space and astro to molecular levels, medical information processing, everything like that is there. And you can start interacting and get a learning experience. If you come to the dome, this is what it looks like. So here's the hat of the building. One of the disadvantages is that this used to be the old power station, and it's a cultural heritage site, so we're not allowed to change anything on the exterior. So you can easily walk by and you don't realize that there's a state-of-the-art dome facility inside. But once you're inside, you get a very nice experience. And now we're going full laser projection system in there with an upgrade that's coming up very, very soon. Now, what is it that I'm going to talk about? Well, it's actually this thing. Now, there's a change in the way that we do science communication and the way that we deal with data in the science communication. And this is all based on the fact that computers are getting faster. You know, the old machine that I bought when I became the head of the supercomputing center back in 1997 was called, it's a nice timing that Anders comes in because he was around at that point in time. Now, it was the Silicon Graphics Onyx 2 Infinite Reality Monster machine that I bought. And the performance of that machine today is the equivalent of a laptop, right? And it was 6 million kronor to buy that machine back then. So that's one change that we have. The other change is the availability of data. That data is becoming available and it's being published by researchers, and we can deal with that data on smaller systems. And we have done a lot of work on visualization and data processing algorithms that makes it possible for me to develop algorithms for medical research, for scientific discovery, and what we call the exploratory visualization. I can use exactly the same data, the same tools, with slight changes to the user interfaces to explain things to children and to the general public. So there's a convergence between what we call exploratory and explanatory visualization, and thus I invent the word exploration, which is the combination of explore and explain. And this is the new paradigm that we're doing a lot of work on right now. And I will try to convince you that this is a good thing to do and that you will benefit, even if you're a hardcore researcher and you're not interested in talking to the public and to the children, doing exploration is a good thing anyway, okay? Now, there are, however, a few challenges in doing this. Now, one of the first challenges that you realize is that even though I have this fantastic, amazing data, and I have really pretty nice visualizations, you're dealing with a generation of very spoiled people. Now, they're kids, and they're sitting at home, and they're playing computer games in the gaming generation, and they walk up to one of your installations, and they start interacting, and it's lagging, you know, because they're used to better performance at home, right? And you just want to walk up there as a researcher and go, hit them in the face, and say, hey, kid, this is 20 gigabytes of data that you're looking at, right? But they don't understand that. Okay? This is a challenge for us. Another challenge is the interaction. It has to be very fast, it has to be very robust, because the kids, they start interacting with things, and if it doesn't work, they interact a little bit more. If it still doesn't work, they start hitting on it until it breaks. So robustness and stability is one of those issues that you have to work a lot on. The most interesting thing from a research perspective is the storytelling part of doing exploration, is that you have to tell people to guide them a little bit through the data and say, hey, here's an interesting point, but I'm not affecting you too much because you're the explorer. You're still the researcher. I'm allowing you the liberty to explore, but I'm just guiding you a little bit. And this is the sort of non-invasive storytelling that we have to do in interactive visualization to engage people. Okay, I'm going to give you a few examples of this, how we do this. So let me start out with this machine. We have the privilege of having dedicated research access to MRI scanners, CT scanners at the Center for Medical Image Science and Visualization that I'm one of the co-investigators on. And this is the machine, the state-of-the-art machine that we have right now. It's a Siemens CT scanner. You don't have to look at all the numbers, but look at this one here. The scan speed is very good. This means that essentially it takes about 3 seconds to do a full body scan. So I put the patient on the table and I accelerate and I go through the gantry, and on the other side I brake before the patient hits the wall. And then I have 25,000 slices of image data coming out of the machine. And I don't know if there are any people in medical imaging here. If you are, you're very familiar with these machines and the capabilities that they have. So a full body scan is about 20 gigabytes of data. And I can even do time result scanning. And then I generate a data stream of about 5 gigabytes per second coming out of the machine. Now, what I do, my task then is, of course, to take the image data that's coming out, the slices, and put it together into full body visualization. And this is what we're doing. So here is a full body scan in 2 seconds and 25,000 slices all the way through the body like this, and I render them. I can even do time result scanning, and this is Anders Persson, my colleague at CMIV, who's a radiologist, and he's sitting playing around with our software and the machines, and while the patient is in the scanner, we do time result scanning. And we do volumetric rendering on the fly. And this is just captured using an iPhone straight from the screen. And you can immediately see things that are hard to realize in static imaging. Is things like the joints, how they're working. Here's a tendon right down here. This is a problem, and this toe is pointing straight up, and it's kind of painful. Now, to get this out into the clinical routine is very hard because they don't have the protocols and the routines to actually start using dynamic data. They're used to measuring things, fixed angles and everything like that, so the diagnostic work is not there yet. Technology is there, but it's not in clinical practice because they're lacking the workflows to use this now. How did I do that? And bear with me, I know that some people you are probably in sort of computer science background and you know everything about visualization and rendering, but you might be curious to know how did I do that. So let me bring you on a little bit of a journey through that. Now, imagine that I have the 25,000 slices of image data here. And of course, my task is to take them, stack them, and turn them back into a volumetric representation of the whole body, and turn that into something that looks like features. What I have is essentially just the X-ray absorption in space, in the three-dimensional representation in the voxel. And this is something that I call the Hounsfield value, which sometimes is normalized to minus 1,000 to 1,000. It tells me how much X-ray has been absorbed in that particular point. Okay. Now, my task is to turn that into something that looks like a feature, like that. How do I do that? This is what we call volumetric rendering. And what most people do today is raycasting. So what we do is that we take the human eye, we take the image plane, we have the data set, and for each of the pixels on the screen, we start shooting a ray through the volume. And we sample the volume as we're going through. So I'm picking up contributions. I'm using something called the transfer function to translate the Hounsfield value to color components, RGB alpha. And then I do compositing along that ray. And of course, I have to do that for each of the pixels in the screen. I have to do that 60 times per second to get good frame rate. Now, of course, this is a lot of math behind this. There's a sort of an interesting problem, and we've been beating ourselves to death for a couple of decades to make this run very, very fast. And the physics behind this is very, very simple. And it's just a standard differential equation that we are solving. It's this one here. I sometimes challenge my students. I say, if you have a differential equation like this, ignore this term over here, and you have this one. What's the solution to that? And they don't get it. 10 years ago they did, but now they don't. Okay. But of course, this is an exponential that you're seeing here. So you have the change. The rate of change is depending on the color, on the light contribution, and the absorption coefficient is over here. This is how much of the intensity that I absorb as I'm casting through the volume. Okay, and the solution is simple. It looks like this. Here's just the intensity coming out of the human eye. Here's the intensity that's coming in, and the absorption is here, and here's the contribution, and it all has to be integrated. Of course, I cannot solve that analytically for these real data sets, so I have to do approximations, and I do that on the GPU, and it looks like this. So here's the actual code that's running on the GPU. And here you can see that I do the compositing. These two lines down here is essentially just doing that raycasting and doing the compositing of the color contributions and keeping track of the opacity down here. So millions and millions and millions and millions of times per second, I'm executing those two lines on the GPU to be able to produce those images that you're seeing. And that's essentially all. So that's all about volume rendering. It took us 15 years to come to these two lines of code. But that's the reason why I need good GPUs. And this is the 980. I picked this is not the latest one that's out there from NVIDIA, but I picked that one because this is what I actually have on this laptop over here. So the mobile version of that GPU is sitting in this machine over here. Just to show you a little bit of the state of the art in this field, here's a case of volumetric photon mapping. What we're doing here is just showering, before we do the raycasting, we're showering the whole data set with virtual photons, and we do multiple scattering and let things bounce around inside of the data volume to deposit energy inside of it. And then I'm picking up those energy contributions when I'm doing the raycasting, and you can see that you get really nice glossy things here, like the vessels that look like plastic tubes. And of course, the radiologists, they hate this because it looks too flashy and too nice, right? So it's not a clinical image, but it's nice for science communication. Other things that we're doing now, just to show you a little bit of the current challenges, looking at the time domain, looking at things like ultrasound and do the volumetric shading of that. And here we're correlating the photon maps over time to minimize the computational efforts in regenerating all the contributions that we have there. Here's an fMRI experiment when we are actually turning the brain into a light source. So where there is fMRI activity, the brain tissue glows itself, because that G of S, the component that you saw in the equation, is steered by the fMRI signal, which is kind of nice. And here's a beating heart that we're looking at. It's kind of noisy because we're trying to minimize the radiation dose when we do angiographies. Now, one of the things that we did, and stepping back a few years in time, is to look at the possibility of doing data reduction, because we're looking at very large data sets. So it's a very simple realization, is that here's a lot of data sitting over here. And in my ray casting, when I shoot the rays through the volumetric data, I'm going to pick up zero contribution from here. Nothing at all, because my settings, those current settings, and I will show you a little bit about that in a while, don't give me any contribution. So why should I even bother with that data? I can just leave it on the hard drive. I don't have to read it in and cache it in anywhere. So just by doing that and developing a multi-resolution structure, I can reduce the data by a factor of 8 to 1. I can tweak my memory budget. If I have 1 gigabyte of texture memory on the GPU and I have 64 gigabytes of data, I tweak the memory budget, and all of a sudden I have a 64 to 1 reduction of data. But my error is growing, because I lower the resolution also in parts where I need resolution. And of course the edges is where I keep resolution to the bitter end. And here's a 200 to 1, and here is eventually a 400 to 1 reduction as well. And then you can see the blockiness. It looks like a poor satellite transmission over here. Okay. Now, of course, there's been a lot of work over the past years, and if you Google all of this stuff, you will find that there's a lot of work on medical volumetric rendering, and I think we're done. I think this is a done deal now. We're sort of the final nail in the coffin on volumetric rendering is putting in now. It's good enough. We don't need more. But what we did, which takes us to the next level, is we took all of these very, very nice multi-resolution volume rendering algorithm, combining it with multi-touch technology, and did some nice user interface design. And now we're going back in time to 2009. I mean, imagine 2009. The iPad did not exist, and the smartphones had just come out. So we got our hands on one of those big touch tables, the first ones that came out. And we said, let's put all this data on the touch table and see what it looks like. And this is what you have. So this is the first video that we put out on YouTube in 2009. And it got viral immediately, because people started saying, wow, it's a touch table. You can do a visualization on this, and you can start interacting with it, and you can dissect data. But as I promised you, why use a video when I actually have a mini version of that touch table right here? Can you see this little screen here? No. But I'm going to mirror it up there, so I just want you to see the interaction that I put in here. So this is the scariest part of my presentation, is switching sources. We'll see. I'll do that a couple of times today. We'll see if that works. Yay, look at that. Okay. Now we're live, and now you are aware of all those algorithms. You think about those two lines on the GPU. They're executing now. Okay, so I'm bringing up one of the first data sets. So this is a scan of a human body. I should say also it's with the greatest respect for people that have died during tragic circumstances and their relatives that I'm showing this data. This is from a person who died in a car accident, in a traffic accident. So, but now we're live, and I have the touch interface here. So and here's a full body with 20,000 slices of image data, and I can start using those gestures that you're all familiar with now. I can zoom in on the details, and I can cut the data from the side. Here we go. And you can see that there's the interior on the body. And what I can do now is to change what we call the transfer function, the function that translates the Hounsfield value to RGB alpha. And now I'm changing that just by doing a setting here. Okay? So I'm peeling off the layers. So all the data is still there. It's just that I'm changing what's transparent and what's opaque. And of course, I can go all the way down to the interior. Now, in this particular case, you can see that what really happened to this this poor individual here is that in the car accident there are multiple fractures all over. Oh, let me show you here. Here's the flashlight. So I'm pretty proud of this one. This is now you can hear how the fan is spinning up on the GPU now because it's doing a lot of work right now. And fractures on the arm up here, and eventually we can very easily find the cause of death over here. You can see that there's a fracture on the jawbone up here, and that means that something probably happened to the neck. So let me cut through the neck like this. There we go. And there it is, okay? So you can see the cause of death, the broken neck right there. Okay. Now, I have a lot of data sets, and I have limited time, but I think I can overrun a little bit, right? Because there's no speaker after me? Okay. I'm just joking, don't worry. Okay. Let me bring up one more data set. Let me bring this one. This is sort of clinically interesting data set. It's a patient, and he's waiting for a heart transplant, and they're waiting for a donor, and the heart is failing. So they decided to put in a heart pump. So let's visualize the heart pump. Oh no. There, okay. Here we go. And let me go straight in here. So here you can see this is open chest surgery. You can see afterwards. And if I cut a little bit from the side like this, there you can see there's the pump. It looks like a vacuum cleaner in there. And it's great because you can do very interesting anatomy teaching as well. So I mean, look at this thing over here. There you go. And if I use the light source, you can get the depth perception going as well, which is nice. You can see the aorta going back there. There are lots of stories to tell about this. But let me switch back and continue the story, because this is just the beginning. Okay. There we go. Yay. Fantastic. Okay. So we got a lot of attention from this, and you know, my wife, who hates me because of the words, she's very critical. She says the only measure she has is The Economist, and she says when they write about you, The Economist, that's okay. The rest of the stuff she doesn't like. So, but what happened here is that this idea of doing large-scale data visualization on touch tables really took off, and we commercialized this. So this is currently the version that's being pushed out by the medical imaging company Sextra, based in Linköping. And I think today we have, let's see, there's about 600 tables that are being available now in 30 countries, running exactly what you've seen here. Primarily used for teaching, for medical teaching of students. And I think that's kind of nice. This is the end of that line. Now I'm going to open up another line. So what you've seen now is the sort of exploratory part, where we are supporting the diagnostic workflow, the medical researchers at the hospital. What about the explanation? Well, here's a person who needed a bit of explanation. This is the Swedish Crown Princess, if you haven't met her. And here's Anders, who's the radiologist that we work with, and here's Thomas, who's one of the people who developed the first version of the table. And this is a nice story in itself, because the Crown Princess said, well, this is really nice technology, and we're going to Shanghai, and there's the Industrial Expo in Shanghai. And she said, well, we need a better presence by Swedish technology down there, so can you bring the table there? And we said, yes, we can. So we did. And here's a picture from Shanghai in 2010, and Thomas, he called me from Shanghai and he said, there are thousands of people outside every morning and they want to come in and work and try out the table. And I was very impressed. I have since been to Shanghai and I realized that 1,000 people is not very much. But what was surprising is that we also got a lot of attention from children who were interested in exploring, understanding data, and they were not afraid of the difficult medical content at all. So that led us to doing a number of installations in different places in the world. So here's the Science Center Singapore that we started working with, and here's the Fields Museum in Chicago, and lots of different places in the world. Here's a picture from the Museum of Technology and Science in Stockholm, if you go there. But the story gets more interesting when you start working with the museums that have their own data, their own scanning facilities. So this is the Natural History Museum in London. And they have amazing scanning facilities down in the basement. And they're generating petabytes of data per week, and they don't know exactly what to do with the data. So we took up the challenge of taking some of the data from the collections. I mean, the galleries are amazing. I mean, if you're into rocks, this is the place to go. But the really interesting stuff is down here, down in the basement. There's lots and lots of stuff in the storage that never makes it out into the galleries because they simply don't have the space for it. So what we did was that we took a few of their data sets, and let me just bring that up for you and give you one or two examples of stuff that we did with them. Here we go. Here we go. So, are there any biology people here? Insect people? No? Well, we do this one anyway. So this is an African bee fly. It's micro CT scanned. And you know, for me, it's kind of nice that instead of having to go to the museum and look at insects that are being pegged to the board, or you pull out those little drawers and look at insects, you can start exploring them interactively. So here's the possibility to now look at the bee fly. It's completely harmless. It looks terrible. It eats other insects. And I have to show off the light a little bit here because I think it's so nice. Okay. And of course, what I can do is to open it up and look at it from the interior. And here you become the explorer of the data set. But I do a little bit of storytelling because I have the info tags that tells you things about what you're seeing and gives you little hints. What is it that I'm going to explore next? But I'm completely free to do the interaction. And of course, I've helped the user by setting the transfer functions in a nice way as well. All right. Let me bring up one more example that I think is pretty cool. This one. This is a piece of amber. It's 20 million years old. So 20 million years ago, a gecko lizard got stuck in tree sap, and it turned into amber. And it's been sitting in there since. And so here you go. So it's in there. So it's micro CT scanned, and there you can see the little shadow of the lizard. This is before we had humans on Earth. And I just changed the transfer function, and there it is. So what I'm actually doing, you can see, there's the bone structure, and all the soft tissue is gone, and the bone structure has collapsed. So what I'm actually doing is that I'm visualizing the negative. So here's the piece of amber. Let me cut through it a little bit. You can see. So what I'm doing is extracting the imprint of the scales in the amber, and that's how I can regenerate the surface of the lizard. So the curators at the museum, they started using these tables and the tools out there in the galleries, and they have something called Science Uncovered at the museum, where the researchers go out in the galleries and they meet the general public, and it's kind of nice. Okay. I don't want to lose all my time, so we'll see. Okay. I can't resist to put in one thing from the British Museum. I'll have to do that. Okay, here we go. Okay, so if you start working with the Natural History Museum, they have 6 million visitors per year. British Museum has 8 million per year, and of course they're one of the organizations that we want to work with. So at the museum they have a mummy called the Gobelin Man. He's 5,500 years old. He's the oldest mummy they have. He's pre-dynastic, and he's been at the museum for about 100 years. They did not know what had happened to the Gobelin Man. They know that he was a young male found in southern Egypt, close to the border to Sudan. This is Daniel Antoine. He has an amazing title, by the way. He's a physical anthropologist, head of human remains. So he's the mummy guy. And of course, what we did was that we took the mummy, scanned the mummy, and put it on the touch table. So courtesy the British Museum, let me show you one of these mummies. And this is the last thing you will see on the touch table. Okay, here we go. Okay, here we go. There. I can leave this machine on out there. If you're into flowers and penguins and stuff like that, you can explore those later as well. So here's the Gobelin Man now. There. Okay. So here you can see things about him. First of all, we can look at cutting from above. You can see that there's a lot of dried human tissue. This is very hard to do in terms of the transfer function because the X-ray absorption is pretty much the same. If you have dried human tissue, it's just the same. The peak in data sampling is very narrow. Okay, so the transfer function setting is very hard to do. Now, but what I can do here is that they were always, Daniel and the curators there, they were very curious about this little fold here in the back. And they were thinking, what is that? Is it just that he ended up in this position? He's pre-dynastic, so he's not been mummified. He just dried in the desert. So is this something, did something happen back here? And they've been looking at that for years. So what we could do, since we had the scan, we could cut him open from the side like this, and we can zoom in, and now you can see the rib cage, and I use my magical flashlight, and down there, actually changing the transfer function there. Here you can see the broken rib cage on the inside. So just inside where the fold is on the back, the rib cage is broken. It turns out that he was stabbed with a knife in the back. So we even found the knife that matches the wound that was found next to him. So we found the murder case, and we found the murder weapon. We did not find the murderer. He's still free. All right. Okay. Here we go. So let me just show you a little bit about the facts about that particular exploration installation. Let me see if I can get my computer back there. Okay. Yeah, so we did an evaluation of this, and this could be interesting for you just to see, because the British Museum, they were afraid that if you have a digital installation in a museum, that it will distract attention away from the real subject that's on display. And this is the worst nightmare for a museum, is that if people are not looking at the real thing, because that's what they want them to do. So so we decided to conduct a study, 6 months in the gallery at the British Museum, and one staff member was sitting there timing the visitors down to every second. How many are here? What are they doing? And then produce a log file of that. And here's just some of the results. In fact, the time that people spent in the gallery increased by 40% after we put in the table there. The fraction of visitors who actually looked at the real Gabbling man increased from 59 to 83%. More people actually looked at the real thing, which was interesting. And the table was utilized 95% of the time. So 95% of the opening hours, someone was interacting with the table. There was a queue all the time. And 60% of the people who used the table discovered the cause of death, which is kind of interesting too. So, of course, what happened is that this is now a permanent installation at the museum. And if you go to Gallery 64, you will find this installation there. A challenge that we're working on now, I don't have too much time to talk about it, but we can talk about it in the break, is how do you actually transfer this? At the moment, we have to work a lot with the museums to help them with the collection, the exploration, the production, and the exhibition. And this whole the data provenance that we work with here is really a key bottleneck in the whole production of these installations out there. How do you enable a research museum with novice users who are not familiar with visualization or data science technology? How do you enable them to actually produce their own interactive installations to bring to the public? And this is what we're working on now. If you want to read more about this, you can read the communications of the ACM, sort of the Science or Nature magazine in computer science that we were featured in the December issue in 2016. The whole story about the British Museum is in there if you want to read more about it. And of course, I couldn't resist to this is the photon mapping of the Gabbling man as well, with the latest flashy stuff. Okay. All right, now we're switching theme completely. And now we need to probably start introducing some other things. Now, this is going back to my original idea about this presentation. I wanted to talk a lot about space. This is the amazing planetarium in New York. So this is the Hayden Planetarium. And it's just next to Central Park. And for many, many years, I've been working together with them on developing software for real-time interactive visualization of space. And to do that both for astro and space research, but also to produce interesting visualizations for planetarium setups. I've been doing that together with this guy over here, Carter Emmert. And here's a picture of him and the inflatable dome outside of the White House. He's just been presenting to the Obama family. And here are actually three of the first students that started working in 2002 on developing this piece of software called the UniView. Now, one of the things, the problems that we had was, of course, to access all the data. And there's been a long-term effort going on. And I talked yesterday in Malmö at the Amateur Astronomy Association. I talked a lot about the efforts that goes into taking data from experiments, from observations, but also from simulations and turning them into a database. And at the museum in New York, they've been doing that since the early 1990s in a database called the Digital Universe. Now, the problem that you have if you're going to visualize space, you need to go, if you want to start off in the sort of real scale of the macroscopic human scale, you start off with the centimeter scale. And if you're at the end of the universe, you have billions of light years. And you run out of precision very soon. So this is one of the problems that we had to deal with very, very early, was to say, how do we actually build in the scale transitions if you're going to make the journey from Earth out to the end of the universe? And we invented something that we call the scale graph. It's sort of a scene graph that builds in scale transitions as you migrate across, and you have a number of different scenes, and that worked quite well. Another thing that we needed to do was the positioning of objects in space. And NASA is very, very nice. They have a system called the Navigation Ancillary Information System that you can query. But we had to do a lot of work to adopt that to do interactive querying, because it's not based for interactive use. And we really wanted to go interactive. And this was a challenge. We wanted to put in planetary surfaces as well. And this is something that we worked on. This is back in the old days when the keyhole markup language was there. And we invented something that we called the geoscope. And that turned into UniView, which was a very nice piece of software. I'm not going to talk about that. But I can do it in the break, or if we have more time later. What I'm going to do is to talk about the follow-up. But you need to know about UniView before you can appreciate the effort that I'm going to talk about now. So this is OpenSpace. It's a brand new initiative. And it's a huge challenge. We have $6 million from NASA to develop this piece of software. And it's a combination between the museum in New York, Goddard Space Flight Center outside of Washington, the Norrköping Center, the Ski Institute in Utah, and NYU in New York, to take the next step in space visualization. And what we're targeting is really to build a platform that is enabling us to do visualization research as such, new methods, new algorithms, new data processing, but also to enable space and astro research using the tool. And at the same time, develop an amazing science communication tool. Can we do that? We'll see. Now, one of the first things that we did was looking at space weather, because the space weather team at NASA do a lot of interesting simulation work. And there's one particular code called NLIL that's generating a lot of data. It's essentially simulating the space plasma from space weather all the way from the sun towards Earth. And then there are other codes that are picking up in the sort of near-Earth area, the BATS R Us, which is somewhere that is doing a lot of that. So a lot of different codes, a lot of different data, lots of different grids, and it's sort of challenging. But we managed to put that into OpenSpace and also with a time resolution. And this is actually from the dome in Norrköping, where we are visualizing the whole solar system and the solar wind through the whole solar system, and doing that in sort of a dynamic setup, so the time is ticking and you can see how the plasma is evolving. And the person who is standing there, you can actually not see him very well in the picture, is actually sitting right over there. And he's going to help us in a little bit. That's Emil Axelsson. Okay. And of course, we did a lot of work on, I wish we would be in the dome, then I could show you live images of the sun the way it was yesterday, because that's one of the things about OpenSpace, is to tap into the resources that are out there and do concurrent visualization of recent information that's being put out there. But what I am going to do is to give you an example of how this science communication exploration can happen, and how we can do interesting events around that. Now, this is a picture taken by the space telescope, the Hubble Space Telescope. This is the best picture we had of the dwarf planet Pluto before the 14th of July in 2015. After the 14th of July in 2015, the picture looked like this. An amazing change. And the reason why we have this picture is because of this space mission called New Horizons. And what I'm going to do now is to try to tell you how that happened and explain that. Now, this is the spacecraft. This is in the assembly hall. And it was launched in 2006. And let's see, there should be sound on this one. We'll see how it goes. Yeah, it's very low here. Now you have to pretend that there is a rocket sound going. Now this launch was one of the fastest launches ever, 18.5 kilometers per second, and it passed by the moon only 4 hours after the launch. To compare with the Apollo missions, it took 4 days to make it to the moon. This was 4 hours. And then it did a gravitational assist around Jupiter to get even more speed, and on the 14th of July in 2015, 9 years later, it arrives on Pluto. So what we did, using OpenSpace, our new software, since it's concurrent, we said, let's tap into the spacecraft. And let's see what it's doing now. And let's see if we can visualize science as it happens. And let's not do it in one place. We'll do it all over the world at the same time. So we had people in Norrköping. We had the mission experts themselves, the people that had designed the experiments, were sitting at the Applied Physics Laboratory at Johns Hopkins. And they were doing live narration during the flyby. We even had a little clay hut planetarium in Ghana connected to visualize together with us. And this is what it looked like. So this is a picture from the dome in Norrköping. Here's me standing down here. We had here's mission control, and then we visualized the instruments and the operations of the instruments as we're flying by Pluto at the same time. I even had Christer Fuglesang sitting somewhere around up here. And we had Neil deGrasse Tyson, if anyone knows of him, sitting in New York and doing the narration. I had to tell him to shut up because he was talking too much. Or I muted him, actually. So this, you don't tell Neil deGrasse to shut up, I'm sorry. Anyway, so this is actually the moment of the flyby. So here you can see so here's the hangout session going here. So this is Orkan, the guy who worked on the lorry camera, and he's very emotional. You know, he's been waiting for 15 years for this thing to happen. And you know, the tears are coming, and you know, the whole world is with him when his instrument is working. Of course, it was kind of disappointing because, you know, we have a delay of 5 hours. So, of course, we didn't get any images live, but we could see what the instruments were doing. Okay, so this made the so Neil deGrasse. I guess I'm friends, and so this is what we did. So Emil, okay, now let's go live. So we will try, and bear with us because we will need to just pull the VGA out. I'll help you. Okay, So Emil is now working with us, and he's the open space expert in Norrköping. You know, we have $6 million in the US, but nothing in Sweden. So I'm extracting some money out of other sources to fund Emil to do the local work here. He needs to reconfigure the screens a little bit before we get it going. So, but it's been an amazing effort in terms of, you know, only 4 years ago we decided, I came up with the name Open Space because I wanted it to be open source. So what you're going to see now is all open source. So you can go back home this afternoon and just download OpenSpace and do everything that I will show you now you can do at home on your own machine, if you have a good GPU. Okay, if your kids have a gaming computer, then you can get that too. So we're loading OpenSpace now, and we will start off by looking at New Horizons. We should probably dim the lights now as much as possible and get used to the eyes. And please don't fall asleep, it's going to be nice. And let's see, as much as possible. Can we get the curtains all the way down to? Let's see if that works. Okay. Okay. So we're in space. Very good. Thank you. Okay. There. Perfect. Okay. All right. Now, one of the things that you really hate as a visualization person is that, you know, projectors, that black is not black. It's sort of gray. It's different shades of gray all over the time. Now, here we go. So now you can see we're in open space. Everything is interactive. Everything is live at this point. Emil is driving it with the keyboard and the mouse over there. And now you can see the sort of little yellow line that's appearing. This is the solar system you're seeing, and you see the orbits of the planets, and you see stars in the background. And those are stars not only in 2D, but in their actual 3D locations, because remember, we're in the digital universe. So we're in the 3D space, all the way out to the Big Bang. Okay? And now we're setting the controls to take us towards new horizons. And let's see if we can do that. Okay. See some nice stars there, the belt of Orion, and there's the Orion Nebula down there. Okay, here we go. Let's keep zooming. Here we go. And here's the spacecraft. Okay. Now we put ourselves, imagine that you're now on the 14th of July in 2015, and we're 4 hours before the encounter. And this is the position. So if we zoom in a little bit, we can maybe look at the labels, so I can tell you a little bit about the instrumentation on the spacecraft. Okay, now you can stay here, so we look at this one first on this side. Okay, so down here you have 12 kilograms of plutonium. Can you turn off the wiggly line? Yeah, thank you. So we have 12 kilograms of plutonium here, generating about 300 watts of power. And those 300 watts are feeding the instruments on board. There's an old RISC processor from 2006. Of course, that's one of the things you have to keep in mind, is that you're dealing with old technology, because it has been en route for 9 years now. And here's the radio antenna that's transmitting signals back to Earth. And if we turn around and look at the other side, you will be able to see all the experiments on the spacecraft as well. In particular, there's one camera that's coming down here at the bottom. You can read it, sort of mirror image down there, called the LORRI. That's the Long Range Reconnaissance Imager. And that's the main camera that's taking most of those pictures that you've seen of Pluto were taken with this camera. Over here you have ALICE, the ultraviolet spectrometer. Here's the infrared instrument. Can you brighten the model a little bit? So here's the student dust collector down here. Yes, thank you. And here's the solar wind experiment. Here are the star trackers that are used for the orientation, and there are 16 thrusters on board that helps you to change the attitude of the spacecraft and point the instruments. Okay. Now, what we're going to do now is to zoom out a little bit and look at the camera frustum. It's a little bit weak on the screen here. This is because of the projector, but this white line that goes here, this is the view frustum of the LORRI camera that you're seeing down here. And over here you can see, here's the frustum, here's the moon Nix, and here's Pluto over here. You can see that Pluto is, the mass of Pluto is not so big, so it's actually the center of gravity of the whole system is actually outside of Pluto. So it's orbiting around the center of gravity over here. Now, if you play time a little bit faster, please, Eamon. Let's do that. Now, so what we're going to do now is to play back the scenario. So this is exactly what happened on the 14th of July. So you can see now the camera is moving. Now it's looking at fixed stars, and it's coming in, and it's moving back and there. And if we zoom in on Pluto at this point, now this is the view frustum of the LORRI camera. This is how those pictures were taken. So you're seeing how the mosaic was built up, and campaign after campaign of imaging was taking place during the flyby. We're now flying at 14.5 kilometers per second, and the nearest encounter is 12,500 kilometers away from Pluto. And it's carefully designed many, many years in advance with small updates en route of the actual kernels that decide which images are going to be taken and at what time. If you fly a little bit faster, Emil, you can see here that here we have this shadow of Pluto stretching out here. And there's a reason why we are visualizing that, because the trajectory of the spacecraft was so carefully designed so that after the flyby, it's passing in behind Pluto and going into the shadow. And the reason why it's doing that is that then we're using the sun as a light source to illuminate the very thin atmosphere around Pluto and do spectral analysis of the composition of the atmosphere. And then you can see they're even more clever. So they managed to actually fly through the shadow of Charon, the moon here, and do the same thing. Okay. I think that, Emil, that's good. Can you actually focus on Pluto again and go in and elevate the map a little bit? Because I want them to see the kind of resolution that we have there. You rotate it around to the sunny side as well. It's great to have a pilot. Okay. And here you can see the famous heart shape that was, of course, made the big news. You know, this the frozen methane over here. And as we're zooming in, you can see the amazing detail that we have of Pluto. And if we elevate the height map a little bit, you can actually see the terrain as well, which is kind of nice. And this is live data. It's all scientific data, and this is a fine example of exploration that, you know, we as laymen can actually use the same data as was collected in the campaigns is available. And thanks to the fact that we have computer graphics and everything like that, we can explore it. Okay, let's give them another example of that. Now, we're just going to zoom out and leave Pluto behind. And there's a very recent experiment going on right now. It's called the Gaia mission. Many of you are maybe familiar with that. The first data mapping out the stars in the galaxy has been coming in from the Gaia mission. It's called DR1 data. That's now available. A few weeks from now, maybe a month from now, DR2 is going to be available. We have 2.5 million stars, and I'm going to ask Emil to just turn them on from the Gaia mission, and we'll see what it looks like. Are you going to Gaia first? All right, okay, so we're going to look at the instrument first. Okay, so the Gaia instrument is sitting in the Lagrange point 2, and it's doing a little nice trajectory around L2 and collecting data from there. And this is not the actual location of it. We're working on that to get the kernels that will give us the exact location of the spacecraft. But we'll see if we can find it. Here's Earth coming into view. And now we're logarithmically slowing down to get a smooth transition to the spacecraft. There it is. Okay, so there's the model of it. And while we're here, can you turn it on while we're here? There, okay. So there's all the data. Now we're just visualizing points where we have data points, so it's not the actual imaging of the stars. But you might even be able to see the grid of the instrument if we're looking at it carefully. Now, let's zoom out and see if we can look at the Gaia instrument from the outside. How am I doing on time, Melvin? Do you have another?
How much more do you need?
10? Is that okay? Yeah. Okay, great, thanks. Okay, so let's zoom out all the way, Emil. And we have to go a little bit faster if you can. So we're accelerating, and I just want you to get a view of the Gaia data from the outside. And of course, you know, this is just the points now. What we will have is all sorts of features about looking at uncertainties and all sort of multidimensional aspects of the data that's being collected. But just for the sake of argument, let me show you the full range of the data set. So we're zooming out, and here it is. And of course, it's contextualized inside of the context of open space. So everything is here, and as we're pulling out, hopefully you will also see it in the context of the galaxy. And so let's look at that. Okay, here we go, and there comes the galaxy. All right. And if you go even further out, you will also see other galaxies, and then we'll look at other data sets, and eventually we will reach the Big Bang. But we don't have time for that now. So, okay, let's go back in again. As a final thing on open space, I also wanted to show you the possibilities of looking at other kinds of data that's been collected. And you know, Mars is a hot topic right now. Our friend Elon is going to Mars, and there's been a number of missions to Mars over the years. And we'll start out by looking at the data that was collected in the 1980s by the Viking missions. In sharp contrast to what we did with Pluto, now we have the possibility to orbit around the planet and capture much more data. In Pluto, it was a one-shot flyby at 14.5 kilometers per second. Going into orbit around Pluto is not feasible. But what we're going to do now is look at some of the data that's been collected from the Martian surface. And if the network is... Now, we're actually loading stuff from the network now, so we hopefully will be with us. Yeah, so here it comes. And you will see that we haven't cached any of this data. So now the Viking data was read in from the server sitting in Utah, I think, at this point. And here you have the Martian surface in front of you. So we'll see if we can zoom in a little bit on Mars. Mars is red because it's rusty, iron oxide, atmosphere, carbon dioxide, plus 20 degrees around the equator, minus 80 on the polar caps, and yeah, all of those things. Mount Olympus, 20 kilometers, 21 kilometers And there's one particular part of Mars, the Martian surface, that we're going to look at, called the Valles Marineris, if we can find that today. We had a bit of a problem finding it yesterday. Let's see what we can do. So I think it's coming up down there.
Working on my Mars geography.
All right. Okay. I think it's down there. Okay. There you go. Rotate it a little bit more and turn to the sunny side.
I think it's coming up right now, right?
Yeah, I think so. Yeah. Okay. All right. Keep going. Yeah. The time controls are not perfected yet on the system here. So we ended up on the night side. Okay. Keep going.
Found it.
You found it. Very good. Okay. But give us some nice light. Okay. Now, so we're looking at now is the Viking data, and the resolution is kind of limited. So we can go down to an altitude of about 16 kilometers, and it looks kind of nice. But with the spacecraft called the MRO, the Mars Reconnaissance Orbiter, we have the possibility to look at data with 6-meter resolution. So we're doing that now. So we're turning on the MRO data. And it will look a little bit patchy first, so we'll see how it goes. Here it comes. So we're reading in, and we're not filling in anything, because it's a raw data visualization that we're looking at, and this is sort of the 6-meter resolution. We've done stereoscopic reconstruction, matching image pairs, so that we can get the altitude as well, so the topography of the Martian surface. And if you go to Valles Marineris, if you ever get the chance, I would recommend a visit to the place called Western Kandor-Chasma, and this is where we're going now. And we're zooming in on that part. And we're reading in data, so the rest it's a bit like Google Earth, but better. Okay, so we're zooming in. And as we're coming in, Emil is navigating well, so we see not too jerky. Okay, and there you go. And now you can see that we actually have the terrain topography with the 6-meter resolution maps as well. We also have a simulation of the atmosphere, which is physically based simulation, so it should be pretty correct with multiple scattering and things like that. So it's sort of state-of-the-art graphics. And you're coming in, and we're getting towards the surface, and let's see where we're heading. Okay, there we go. And now, here comes the surprise for you guys. Now, there's one instrument on the MRO called the high-rise camera, which has a resolution down to 25 centimeter. So this is one example of what we're going to do with the reconstruction of the data. So here we have 25 centimeter resolution of the Martian surface for you. We have only showed this a couple of times, so it's a little bit of a world premiere with open space for you. And now you can see with a nice atmosphere simulation, and I swear if Matt Damon was here, you would see him now. And now we're down. Now these sand formations down here, they're maybe 25, 50 meters in altitude. And you can see the interesting flow patterns and the erosion on the Martian surface like this. If you stop a little bit there, it might kick in some more resolution. Thanks. Yeah. And of course, we're free to rotate around. And as a grand finale on this little scene here, maybe we can give them a nice Martian sunrise or sunset or something in the Valles Marineris. Okay, you see the stars. This is the Gaia data that's rotating over there now. Okay, so and let's see, time ticks, and now the sun is setting. Okay, sunset. Great, beautiful. So I'm challenging Elon Musk. Why would you want to go there when you can go virtually? Okay. Great. Okay, thank you, Emil. Thank you. Give him a hand of applause. He did a good job. Let's see, where are we? I need to figure out where we are. Okay, I just need to wrap up a few things that I wanted to tell you about. So let me see. Okay. How many minutes? Am I running out? 2? 3, 4, 3 minutes. Okay, let me do this way. What I really wanted to do, I have a lot of other things that I wanted to show you. I have the microcosmos visualizations and things like that too, but you've seen a bit of that now. So one important thing that I wanted to put across to you today is this thing here, and this is a call to action for some of you. So this is a project called Wisdom, and what we are going to do, we have a large donation from the Wallenberg Foundation, 150 million kronor. You've seen what we can do with the exploration concept, what we can do in a dome theater, but also on touch tables and all sorts of aspects of science. Doing the communication is actually quite rewarding, even if you're a hardcore scientist and you prefer to spend your life in the equations, every now and then talking to kids is fun, right? And we do a lot of that. So what we are going to do now is to expand this concept. We are going to build domes or visualization environments, at least one in Malmö at the Tekniska at Malmö Museum. One at the Universium in Gothenburg, one at the Museum of Technology in Stockholm, and one up at the Lund University, and tie everything together into one concept where we're going to share information, share visualization work, but also all sorts of data resources to reach out to about 1.5 million people per year in the country. And we're working together with the Singapore Science Center and the American Museum of Natural History as international partners in this. So what we need is, of course, a lot of support. And you might be contacted by, for instance, the people in Malmö. I know that there are some people here in Lund who have similar thoughts, and we're definitely open to including more science centers and science communication parts in this. But it's all depending on this circle of going from visualization, technology research, application research, and bringing it out to the audience and then bringing it back in again. For instance, an example is the visualization of New Horizons that we had. When we actually brought a team of scientists on the team into the dome in New York, and they had a team event, some people were, aha, this is what we're doing, because they didn't have the grand picture, right? So for team communication, doing these kinds of visualization work is actually quite important as well. The final picture that I want to show you is this one. Similar to the event that we had yesterday, but in the dome in Norrköping about 2 years ago. They called me on a Saturday morning, and they said, Anders, you have to come in, because we have 50 amateur astronomers from Örebro coming. And they're hardcore. They're really like, they had sent a list of details. So they want to see this galaxy and this star and discuss this and that. And no one else wanted to talk to them. So, so I said, okay, I'll come in and talk to them. So I set up in the dome and I used the software and everything. And then I see in the back row there's families with kids. At the center, they had sold tickets to the show to kids as well. So I had 6-year-old kids and I had amateur astronomers with an age profile of 70 plus. Okay. So the challenge is, can I use visualization to communicate both to 6-year-olds and to experts in a domain? So what I did was that I started out and I showed a little bit. You saw the solar system that we have there. I showed the solar system. I talked a lot about planets, because I thought the kids, they will appreciate planets. They know about planets, right? But then I spent most of the time talking about galaxies, because they had a list of galaxies that they wanted to see. And afterwards I felt very guilty, because the kids are like, God, enduring 45 minutes of galaxies. So I walked up to one of these kids and I asked him, so I'm sorry, it was probably very boring for you, but I hope you appreciated the planets, because you know about planets, right? And then he looks at me with big eyes and he says, I know about planets, but galaxies, that was cool. So a lot of people have contributed. Here's a few of the names. I'm just a proud representative of many people's work, both in the medical domain, everything else that you've seen, and in the space domain as well. So it's their work, and I'm really proud of presenting that, and I'm very happy that you spent an hour listening to me. Thank you.
Thank you very much for a fascinating talk. Do we have questions?
So I'm wondering about these advanced medical imaging techniques. Every day, not every day, but if you read the news, you always read about how computers are so much better at diagnosing, or they're getting better, and it looks like that will be the future of diagnostics. So are these advanced images a superfluous step for the computers, or will it be a necessary part of the future as well?
I mean, it's a time of change. Things are changing, and what I have talked about here is what we have done so far. I would say that much of the work that we're doing now is moving in that domain. How can you deploy artificial intelligence, learning algorithms to improve the diagnostic workflow? We have a new project in artificial diagnostic work. When it comes to image processing, you're seeing all the time algorithms are getting better and better all the time. I think there's going to be a lot of advancement of diagnostic work, but there's also going to be a backlash in cases when you reach failures. Because we don't really understand what's going on inside of a learning algorithm. It's very hard to predict what is correct and what's not, and there's a lot of research needed on the sort of the understandable, the explainable AI aspect of what we're doing. So I'm a little bit of a skeptic when it comes to saying this is going to solve all the problems that we have. It's going to change many things. One of the things that I think, in the past we've seen, in the first wave of AI, it was primarily looking at reasoning algorithms. It was sort of procedural expressions and things. The second wave now is the learning. And machine learning, deep learning is hot right now, right? I think that the next wave that's coming after that is going to be put the human in the loop again. So interaction and understanding of AI, the collaborative aspects, AI in harmony with the human. And there are these nice examples with chess computers or Go computers. But if you add human intelligence on top of artificial intelligence, you're going to be better than artificial intelligence. So there's a room for the human on top of that. And I think that's very interesting research: is how do you interface how do you put the human in the loop in all these intelligent systems? Then if you start talking about singularities and stuff like that, then it's a different thing, right? But I think that's pretty far away. So, but for the time being, I wouldn't worry too much. There's going to be a need for humans in the loop. But we will be interfacing with them in different ways. And I think visualization is one of the most powerful ways of interfacing the human with the artificial intelligence, because you reach a visual language and you start maybe communicating at the semantic level. And I have a 1-hour presentation about that as well, but I'm not going to do that today.
Just a quick question. You started off with magnetic resonance images.
Yeah.
And there's a project here in Lund on that as well. How strong is the magnet?
That was the CT scanner that I showed. We have the 3 Tesla machine. I mean, yours is much better. 7 Tesla is what we would like to have, but we don't have that. But of course, it's a national facility.
So the data rates of the machine here in Lund are very higher than what you showed?
Right, yes. But it wasn't MRI, it was CT.
Ah, okay.
Yeah, yes.
So what I've seen of open space is that there's a lot of work still to be done before it's launch ready. Are you actively using it in front of audience in the dome, and how much?
I just did in front of you.
No, but I'm saying, it doesn't play videos, it doesn't have rendering capabilities, it's still a version 0.11 on the website.
It's a beta version that's out there for testing.
Exactly.
Yeah.
So how far are you from actually marketing it to Planetaria, and are you going to be doing that, or is this also always going to be something you run alongside the official, the more established planetarium softwares? And
you mean like UniView? I think the future will tell. I mean, our ambition is to do a lot of interesting research in the context of an open source project, and it's up to people to pick that up and turn it into something that is a production level software, and it's not right now. It might be in the future. We'll see. But I mean, you can do that.
I have nothing to do.
Yeah, I think we should maybe then move on to the next speaker, and let us thank the speaker.
Great. Thank you. Right.